our next speaker is Dr. Giovanni Spampinato, and Giovanni is an experienced geophysicist with project management background. His expertise includes processing and interpretation of geological and geophysical data, 3D modelling and inversion, resource evaluation and targeting. Giovanni aims to create new knowledge and methods in the field of 3D geological modelling through an integrated approach, mitigating the geological risk in resources, discovery and management. So, please welcome Giovanni.
Just a sec. Yep. Hi everyone, and thanks for having me. Today I'm going to show you some outputs from the Stuart Shelf 3D model. And first of all, I would like to acknowledge and thank all the people in CSIRO, my colleagues that worked on the Stuart Shelf project. And this model is just part of this larger project led by Susanna Schmidt, she's here, which aim to better understand this stratigraphy, which includes the style, the distribution, the topography and thickness of those units making the Stuart Shelf, particularly some key lithostratigraphic units that might control copper mineralization in this part of the world. So first of all, the constraining data for the construction of the 3D model includes well data and surface geological map sourced from CSIRO, and then also some depth of the Gardner diorite from geophysical fault models that Clive Foss did as part of this project, and also the dam which has been sourced from GATS. So if we take a look at the model, the top of the model is constrained by the dam, the bottom of the model by the top of the crystalline basement, and above the basement we've got 8 different formations. That includes the Pandara, Tapley Hill, and Whyalla sandstone that are those key lithostratigraphic units I was talking before. So if you already played with the existing version of the Stuart Shelf 3D model, this refined version has some differences. So for example, the updated version extends a little bit further west and honors, of course, the lithological data, the well markers, and also the outcropping units for each units, of course. I wanted to show you that because basically what I did was importing those outcrops as a shapefile into GoCAD, and those became point sets along with the markers, and they constrained the construction of each surface. There are a couple of differences. We are looking at the Tapley Hill formation. The white surface is the previous surface, and the bluish surface is the new one. There are 2 main differences, especially in the central part of the area of interest and in here, which I think that there is a extension of the Tapley Hill formation. I wanted to show you that because I wanted to show you my reasoning behind the construction of this surface. I might be wrong, I'm open to discussion about that, but we've got, for sure, drill hole data that tell us that there is Tapley Hill formation. We've got extensive outcropping Tapley Hill formation to the east, and just in between, we've got also accumulation space. There is actually a major depot center over here, and there is lack of data. When there is lack of data, it's not that there is no Tapley Hill formation, it's just that you have to come up with the most likely scenario. And to me, it seems logic that the Tapley Hill formation would extend in this part of the area of study. Now, when I say that there is no constraint data, this is a problematic picture of the 3D model. So if you look at me, that's basically a side view. We look at the surface, that's the Tapley Hill Formation, and on top, we've got, where are you? Oh, okay, we've got those drill holes, these ones, and these ones. And unfortunately, these drill holes are too shallow, and so that's why we don't have data in this part of the area of study. And again, there are some minor refinements and adjustments. So with the drill hole data, in here, gray dots are basement markers. Green discs are Tapley Hill Formation. Unfortunately, in here, you don't have Tapley Hill Formation. That's the old surface. And you end up with the basement on top of the Tapley Hill. So in this part, we are in the central part of the area of study. The top of basement is pretty well constrained. And in the updated version of this 3D model, that piece of constrained data has been honored. And lastly, if we move to the center, there are a bunch of drill holes in here that tells us that there is no Tapley Hill Formation. When this happens, sometimes you have to go back and double check the original data, because when you import the data into GoCAD, it's very easy to make mistakes. It happens. So good QA/QC, going back and actually looking at the drill holes and making sure that from the tertiary cover, you jump straight to Tonyan and basement. And so actually, yes, there is no Tapley Hill Formation in here. Since I have just 15 minutes, I chose to talk about the 3D model per se and not the geological observation, because I think that I want to raise interest in downloading those products to take a look at the outputs from the Stuart Shelf project, and to make you understand something. That's one surface, once again, the top of the basement from the 3D model. Look, it's cool to play with, but if you are not familiar with 3D modeling, if you don't have a GoCAD license, which is expensive, that's next to useless. However, this is a 3D object. It has all the information that we need. We need just to extract that information in a useful way. And one example is to make grids. We are more familiar with grids and maps. This is, for example, top of the basement depth. We can make topographic grids, thickness grids. We can import them into ArcGIS, so it's easier. And with 3D, we can also combine. So we create grids with, this is an example of a combined top of basement plus Pandara, Apilati Light, and Tapley Hill Formation. And that helps, for example, if you want to know the base of a certain lithological unit. With a 3D model, you can actually do that. So I've created that for, once again, that's the example from Pandara, Tapley Hill, and everything else. And that's important because with 3D modeling, you can actually analyze and understand the topography, the thickness, the lateral continuity, and make aerial computations, so numbers. Out there, all they care about is numbers, is quantity. And you can do that from this surface of lithologies that are undercover. The other added value when you've got those bunch of surfaces is that you can create a volumetric model, voxets. So first of all, you can make this time volumetric computation of an horizon, of a deposit, prospective rock, an aquifer, you just name it. And that's very important. And secondly, you can also create cross-sections in any direction, and you can analyze sedimentological styles, structures, and so on. And that's the other added value. We are all familiar with cross-sections. And I like those cross-sections because even though I did not include faults in this 3D model, you can tell that there are sharp variation in topography or thickening of these units. And some of those correlate with mapped faults. Now, in the early stage of this project, it's been concluded that there is a high fault density. It was very difficult to identify the faults that were active and that controlled deposition of the Stuart Shelf. So that's why faults haven't been included. But I like to think that, with this 3D model, this can help in better understanding the role of some faults, along with maybe new data, new AEM data, for example. And lastly, I wanted to talk to you about inversion. So after I finished this project, I noticed, for example, a correlation between the Bouguer gravity anomalies and the thickness of the units on top of the basement. This is, for example, a grid of combined Brighton, Vialla, and Icaran formations. So if you look over here, there is a good correlation between the gravity signature, this gravity ridge, and thickness of these deposits. However, on the contrary, you've got an inverse correlation between the basement topography, so the deeper it goes, and still you've got these positive anomalies. And so my question was, is it possible that the units overlying the top of the basement are responsible for the gravity signature of the area? If you look at the intensity of the grid, this is a silly question actually, but I just wanted to have a little bit of fun with inversion. Yeah, that's an even better example. So we are looking from below. You've got thickening of the units above the basement. The basement is, of course, the horizon in red. And you've got these positive gravity anomalies. Same in here, positive gravity anomalies. So I chose two areas in the central part of the area of interest. And I performed unconstrained inversion. This is the lithological model just for reference. Unconstrained inversion means that the software is just free to create a density distribution that matches the observed data. And the conclusion, along with I played also with Euler deconvolution, is that the source bodies that were at depth from 5 to 16 kilometers are responsible for the gravity signature of this part of the world. And then I've included actually the lithological information. So this, maybe I don't know if you can tell, but this actually is an inversion with lithological boundaries. I tried different configuration about the starting densities, and all the inversion results converge towards these results, which says that the basement is heterogeneous, first of all. So if you try inversion with an homogeneous basement, and we tried that in the past, it just doesn't work. And also that the basement at times is less dense, so it's 265 to over 3 grams per cubic centimeter, is less dense than the overlying units. For example, you might have a felsic intrusion. So what I'm trying to say is that with inversion, with 3D modeling and inversion, you can better understand the nature of those units undercover, and you can also refine. We've got excellent products, but we go on with technologies, we acquire new data, and we refine the understanding and the mapped interpretation of all these rocks undercover. Thank you very much.